our keynote speaker, Dharma Shukla, who is a technical fellow at Microsoft working on a new AI system called Singularity that I've heard a lot about inside of Microsoft, and you probably haven't. Before that, Dharma was the originator, designer, and driving force behind Cosmos DB, which is a global database that Microsoft introduced. I believe it was 2 or 3 years ago. And it's a really cool system and really important and to Microsoft, and it's rapidly growing. It's widely used both inside Microsoft and by Microsoft's Azure customers. Dharma joined Microsoft in 1999 and contributed to various products and services, including in addition to Cosmos, Azure itself, Live Mesh, and others. He specializes in distributed systems and earned his master's degree in computer science from the University of Washington. So that's about all I have to say for introduction, other than I'm sure it's going to be a great talk. And I guess we can begin now. Dharma?
Thank you, Leslie, for warm and kind words. And thanks everyone for attending this morning, or whichever time zone you are in right now. So I thought today I'll talk about my experiences in applying TLA Plus in the last couple of projects I have been working on at Microsoft, and especially talk about how we incorporated TLA Plus in the engineering culture. I'm assuming this is a group of TLA Plus practitioners. So you would all be able to relate to spreading the TLA Plus in the community, and how you can incorporate it in the engineering teams or your teams that you're working on. So the outline of my talk is I'll talk about a couple of systems to give you the background of the complexity and the kind of problems that we were trying to solve in these systems, and how we applied TLA Plus both as part of the design of different subsystems of these larger services, but also in terms of customer-facing artifacts, like the service level agreements that we offer to customers, and precisely specifying those agreements in terms of TLA Plus specs. I'll talk about things that have worked successfully. Of all the things that we've tried, I've harvested a few of these lessons which I learned, and things that were successful in, especially in medium to large teams. And then a quick summary. So in terms of example systems, I'll start with Cosmos database. It started as an internal project called Project Florence, because it was prototyped in the beautiful city of Florence, and in 2010. And it was a very unique project because it started grassroots within a large company like Microsoft. And the vision that we had back then was to create a globally distributed database, and the motivation for that was to meet the needs of internal applications at Microsoft. Over time, it grew. In 2017, we launched it externally, and it is a ring zero service, which means that it is at the bottom of Azure stack, and many other services, both inside Azure, in Microsoft, including things like Teams, and other parts of Microsoft. They use it heavily, and also external customers of Azure use it, and for mission critical workloads. When we started out, we had a very stringent set of requirements from the large scale applications inside Microsoft. I'll just enumerate a few of these goals for you to appreciate the constraints that we were working against. So we wanted to elastically scale throughput. As a horizontally sharded database, there is always a need to scale storage, but we also had the challenge of scaling throughput, and that too elastically across any place in the world. So a retail customer may want 5 million writes per second in one region of Azure, and has some other application, or the same customer wants 3 million reads in another region. And then as time passes on, these reads and writes have to fluctuate elastically based on the specific workload. And we have to do this elastic scale up and scale down of throughput within a tight budget. It cannot take long periods of time. So partition splits and merge, and those things have to happen really instantly, while the database as a single system image distributed across many regions. The other thing was that we wanted to deliver stringent SLAs on latency for reads and writes at P99 across anywhere in the world. And so that meant that we have to navigate the cap theorem, and that meant we had to make sure that we can offer pragmatic consistency choices to trade off latency, availability, and consistency. In terms of high availability, because it was designed as a multi-master system, customers expected read and write availability. It was paramount because Microsoft's billing systems and many of these mission critical workloads were dependent on it. As I mentioned, we decided to offer tunable consistency models. So between linearizable consistency and eventual consistency, intermediate click stops. And I'll describe how we employed TLA Plus in defining these consistency levels. And then also equally important was that we have to operate the service at a really low cost, so that we can offer it to customers at a lower price point, and also save COGS for internal customers at Microsoft. Then because it is a multi-tenant system where we densely pack many workloads on the same physical machine and across machines in a cluster and across clusters, we have to give not only security isolation across different workloads, but also performance isolation. And it can get tricky, as you might imagine, when the system is being used for both transactional workloads as well as offline use cases. So that also required an additional level of constraints in terms of how we isolate workloads, so that every tenant feels that they got effectively dedicated cloud capacity. But in reality, we are multiplexing thousands of tenants across the same physical capacity, and still making everyone, all customers, feel that they're the only ones who has this sort of illusion of infinite capacity at their disposal. Customers wanted to evolve their schemas very rapidly and agile manner. So and they wanted SQL-like queries over semi-structured data. So that also caused a lot of challenges in the design of the core database engine. And so against these constraints, we had to design the system and deliver it in the time frame that we had set out to. So as you can imagine, a very tight design space which we had to navigate, and we started in 2010. Millions of lines of C++ code later. We built the system, and it is proven to be a very robust system that many other customers and other services have taken dependency. In terms of just a quick, very high level overview of the system model, there are many tenants of Azure. Every customer is a tenant. They create tables, collections, graphs within a database. These things effectively translate into what we call containers, which are logical collections of different entities. And then each container is partitioned in a two-dimensional space. It is partitioned horizontally, like a traditional horizontally sharded database, but it's also partitioned across regions. And so each partition is this circle that you see on the screen consists of a replica set, and as you can imagine, that gives high availability. It implements Paxos-based replication. There's a leader, so it has leader election and the replicated state machine implementation. Leader receives the writes, and because we wanted to, we have a very tight budget of system resources that we want to optimally use. We distribute those system resources in a specific budgets of these resources to the leader and the follower. So that and we route the writes and the reads such that the system overall is balanced and all the underlying resources are utilized across all the tenants optimally. So reads are directed towards the followers, and the writes go exclusively to the leader. There's a special a follower. It's called XP leader. It is responsible for replicating it cross partitions. And the next level of agreement that we have to build is across partitions in a partition set. So just like a replica set constitutes a partition, there are multiple partitions. They collectively form a partition set, and that is required for globally distributing these partitions. The same partition is a workhorse abstraction because it's a highly available and a reusable entity. We use it for partition splits, merges, in addition to global replication, cloning partitions on demand, as well as streaming on demand. So, in a nutshell, as you can imagine, resource governance, the replication protocol is a resource-governed protocol, multiple layers of consensus, and it is at a scale across hundreds of thousands of customers, and there are a variety of workloads. And still, we have to make sure that all of the guarantees that I described in the previous slide, they hold true. So in this system, we apply TLA Plus across in many parts of the system. But I'll talk about a few notable ones that are externally visible to the user. So the most notable one is is defining the consistency levels. Because we are a globally distributed system, we wanted to offer service level agreements, not just for high availability, just like most cloud services do, but we also wanted to provide service level agreements for consistency, latency at P99, in addition to high availability. And so um, when it comes to consistency, as this picture shows, there's a wild west of variety of consistency models that have been defined, and what we wanted to do was, and the state of the art when we started Cosmos DB was, on the one extreme, strong consistency, or on the other extreme, eventual consistency. And what we wanted to do was we wanted to codify of this wide variety of consistency models, the ones that are practically useful to customers. And after a lot of experiments and flighting these consistency models with internal workloads, we identified a few of these which could be precisely specified, whose guarantees could be provided to customers, and in a manner that customers intuitively understand those guarantees, and they can build their applications in a predictable manner. So they don't have to settle for eventual consistency. If they wanted weaker guarantees, they can settle for these other 3 consistency levels. And also, because of the way these consistency levels are implemented, it has a concrete impact on the bill or the pricing model of the system. So when you configure your consistency level as strong or bounded staleness, you get half the throughput of your reads and writes for the same price. On the other hand, if you configure session or consistent prefix or eventual, you effectively get double the throughput for the same price. So there's a cost difference in making that choice between these consistency levels, and that is that also we sort of dissected what attributes to this cost in a multi-tenant setup. And so in order to try out these different consistency models that that have been there in the literature, and then identify the ones that actually are practically useful for customers, we use TLA Plus heavily. And even talking to internal teams and explaining them the consistency models and what they meant to their applications, TLA Plus was godsend in terms of communicating the guarantees in a precise manner. And so when we eventually released Cosmos externally, we wrote the TLA Plus specs for the 5 consistency levels that we ended up exposing to the users, and in a manner that makes sense for the application user, and not without abstracting away all of the details of the implementation of the replication protocol and such. So that's one concrete customer-facing artifact that happened. We also learned that while TLA Plus is awesome in terms of describing precisely capturing the design intent and then debugging the design, we wanted to make sure that whenever there is a violation whenever there's a drift between the implementation and the design, we can catch it. So we ended up, for the consistency levels and giving SLAs around it, we ended up building a consistency checker service, which would maintain the history of all the transactions, and make sure that whenever there is a consistency violation, we could detect it, and we could give customer their money back. Happy to report that sans the early days where we were prototyping and using the system internally at Microsoft, we have not had any violation in the consistency SLAs after we launched the service. And so there's an entire system that runs that also uses Cosmos DB internally and does this checking of any violation, both for availability as well as consistency. But so this was we found in the early days that while we knew that we had a robust design which we had debugged and implemented, we without sort of these checks and balances, we were not sure whether there would be any bugs that would be discovered later. And so this system, which is an online system continuously running in the background, helped detect it and report it to customers in time. The other thing that we did was we also applied a probabilistic bounded staleness, which was a work done a few years back to give to expose the matrix to the customers in a way that even if customers had chosen weaker consistency model, in practice, if they were getting stronger guarantees for their reads, we would report based on their workloads, based on their regional preferences, and report propagation delays across regions. So we transparently exposed all of these metrics related to consistency to the users, but everything sort of started from precisely describing those consistency levels using TLA+. Let me switch gears and talk about the system that I'm working on currently for the past year or so. This is a globally distributed AI system that efficiently schedules resources, and it relies on transparent preemption of long-running programs or jobs. And one of the things that we do is, in order for scheduler, this is a distributed scheduler, and it is capable of transparently preempting any program at any point in time without requiring any cooperation from the users or the programmers. So this requires taking a consistent snapshot of those programs midstream while they're executing, and then suspending all of the program state and then resuming it at a later point in time, perhaps in another region, in another cluster, definitely on some other machine. And here, in terms of resources which are being scheduled, we're talking about hundreds of thousands of AI accelerators, processes running on CPUs and network, all of the system resources. And the constraints that the scheduler has are around finding the best topology. So whenever any program is suspended and resumed later, it has to be resumed against resources which yield the best performance. And each program has its idiosyncratic requirements about how the resources are assigned to it, and the topology and the placement constraints. So here, having used a TLA Plus successfully in a large team in Cosmos, we while we're starting out this project, I'll talk about the team and the awareness of the team on TLA Plus in a few minutes. But we started out by doing all the design work in TLA, and one of the problems that we found a very interesting and a novel use of TLA Plus was that in this example, we had we wanted to do a consistent snapshot of the program state, which is a program is distributed across many machines. And in order to get consistent cut, we wrote the TLA Plus for Chandy Lamport. We had two other algorithms because we had to do a coordination across device state. Or by device, I mean GPUs and FPGAs and such devices, as well as processes which were interacting with those devices. And while we are doing the snapshotting, we have to honor the programming model guarantees. For example, MPI programming model requires a program order guarantees in a certain way, and we had to honor those guarantees so that the application programmers intuition doesn't break, or they don't have to do anything special to deploy their programs onto the system. So we tried two other algorithms, a tandem collective algorithm and a queued collective algorithm to devise an efficient mechanism for doing consistent cut. And what I learned was that TLA Plus, because we wrote TLA Plus specs for all these three different algorithms, and we debugged the trade-offs, and we found that just by writing these specs and it made very apparent in terms of the difficulty of implementation or maintaining these three implementations of these algorithms. And so without writing a single line of code, we could evaluate the trade-off as a team between the choices that we had and against the constraints that we were trying to build these, implement these algorithms. So that was a great insight. It saved many months worth of engineering effort, because we could look at the trade-offs and discuss them with precision. And it eliminated all subjectivity, and the trade-offs became very clear. The other thing that I see happening in this project is that this is a massive effort across hardware and software teams, and we have to communicate the design to so many different people who have completely different context, and they're working on different parts of the system. And TLA Plus has been helping us in terms of communicating the design to teams that are not, directly associated with the specific subsystem. So that also is in addition to all the things that I had learned about TLA and its application, in the cultural context while building Cosmos. I found this was useful here. A few things I want to, things that have worked in terms of applying TLA Plus in a team. I found that hiring engineers with the TLA Plus background has been like when we post job descriptions, we say, knowledge of TLA Plus is preferred or would be great. And this is an example of an engineer earlier this year who applied for a position, and he said, I've been using TLA Plus, and shared some of his specs. And then so that was great, because we could tell that this engineer has worked on this type of systems. It's like reading the code to understand the sensibilities of an engineer. Here we could read the TLA Plus spec and sort of even before the interviews. And obviously this engineer was a great hire. He's been contributing and responsible for one of the critical components. But this approach of hiring engineers with the background has worked. The other thing we have done is, in order to spread the understanding of TLA Plus within the team, one of the things that has worked is when we onboard a new hire on the team, we have a team wiki, and we upload all the specs. So people contribute to TLA Plus spec. There's a Teams channel where they discuss the specs that they have contributed, and so this has also worked. The third thing that we have done, while Singularity is too nascent in Cosmos and other parts of Microsoft, is that whenever we have an outage or a SLA violation, once the teams identify the root cause of the bug that contributed to the issue, we associate a TLA Plus spec with the fix, which everybody can review, to make sure that because it's high pressure situation where we have to fix the bug in a short amount of time, and making sure that the fix doesn't violate or introduce new correctness problems. TLA Plus has been applied, and I think this is documented across some of the incidents that have happened in Azure and elsewhere as well. The fourth thing is SLAs, service level agreements. A lot of services, cloud services, claim that they give this guarantee or that guarantee, and they usually play with the law of large numbers, where there's no per customer SLA, but in the aggregate, the SLAs are met. So having a TLA Plus spec to clarify exactly what guarantee is being, is included as a part of that SLA, and precise description of that goes a long way. That we learned by using TLA Plus for the consistency SLA in Cosmos. So in a nutshell, tremendous value in terms of upfront application of TLA Plus while designing the system. At least all the critical pieces of critical components and subsystems applying TLA Plus. Also making a part of the model engineering culture goes a long way. And it has been applied, TLA Plus has been applied successfully in not only these two systems that I described, but in Azure networking, Azure storage, and many other teams across Microsoft and elsewhere as well. So thanks.
Okay, thank you, Dharma. I looked at the schedule and discovered that there's no ending time for this session. So we can go on forever, at least until Monday. Perhaps we'll stop a little bit before then, but that does mean that we have plenty of time for questions. Now I will turn this over to either Stefan or Marcus, who will better know how to deal with questions inside of Zoom. So which one of you will take it away?
Well, I can give it a give it a try. So as I mentioned on the chat, I don't know if you saw that. So you may ask your questions in the Zoom chat or also on the individual hallway. But I don't see any questions there for the moment. So it's easiest, I mean, if you just speak up or raise your hand in Zoom if you want to ask questions.
I have a question.
Please go ahead.
Hi, I'm Shuham from Shopify. We also use TLA Plus to do some systems, but not as far as what you have done. Thank you for the talk. It's been really great to hear other companies apply this stuff successfully. So I have a couple of questions surrounding, you talked about efficiency gains. And I think at one point you talked about that when you offer, when you choose to have a stronger or weaker consistency guarantee, you use the word double or half of the performance gain. And I was wondering if that is calculated directly from the TLA Plus spec, or if that's calculated from like a separate, like experimental measurements or some other inference method.
That is a function of how much resources we are willing to distribute to different replicas within a partition and across partitions. So that math can be tweaked, and you can reason over why by changing some numbers you get different throughput, because there is an application of Little's law in the queues that we maintain, and how the budgets are allocated in this resource governed system. But that's not the part where the TLA plus. Of course, you can write a TLA plus spec to validate the assumptions, but that is a well-defined formula for how the budgets have been allocated to different replicas.
Thank you. And I just have like one more quick question about TLC in specific. You mentioned that you write out a lot of specs and you kind of work with the specs quite a bit. And you had a slide about TLC checking accompanying postmortem. How widely used is TLC, and like do you guys run these TLC in highly like concurrent, like with multiple machines or something along the lines? Like, can you offer some insights on that?
We do, and I see that we have Vaibhav also. Vaibhav, do you want to talk to it? Vaibhav is an engineer. Let me introduce Vaibhav. He's an engineer on the team. Yeah, Vaibhav, go ahead.
Yeah, so there are models where we had to run, like in past, I have run TLC in a distributed setting and let it run for a week or so and catch edge cases. But in most of the cases, if you split your design to small specs, and then interaction is based on contract exposed by specs, each spec can run pretty fast. So for example, in the singularity world, the specs we have written with right size, with the size we want to experiment, we were able to complete the run within an hour or so on a regular desktop. So it depends. I mean, if you have to, you need to plan it early on how you're going to write your model. If you're able to split contracts and interaction between components very clearly, and then validate each individual in a greater depth, and then write a separate model as an aggregate to see that if contracts are followed by each component, will the system coming together work as a separate model, then you wouldn't need to run in a very large setting. Generally, those models are very efficient and can finish very fast. But if you split the whole thing and build a one model which represents the depth of system, in that case, it will have a very large state space. So then it can keep running for a long time. In general, longer you run your model, more nines you are getting, more accuracy you will have in your system when the model you have written doesn't finish fully in reasonable time. That is how you should see. So there are cases where we had very large model. We caught most of the bugs within a day or two, but then we let it run and it complained after a week or 2 weeks, and then we found some real issues that we were able to address after that.
Thank you. And just sorry for taking all the time. Just one more quick question. Have you guys experimented with proofs or anything other than that for your work in addition to TLC?
No, I haven't experimented with proofs.
Thank you.
There's a question by Lazaro. You want to speak up? Otherwise, I'll just read it.
Hey, hi. I was just curious about the use of PlusCal, because I found that it's hard to talk to first-timers about TLA plus, but PlusCal sometimes it's easier because it looks more like a programming language. I just wanted to see what was your experience, if there was any.
Yeah, I think Cosmos DB PlusCal was used quite a bit, but we have folks like Vaibhav who are well versed with TLA plus and enjoy authoring specs directly. I think it depends on the engineers, but we've kept it quite open.
In my experience, I started with PlusCal. It was much more familiar, similar to C syntax. But I realize it's kind of a stepping stone to get used to TLA plus. You can write specs really well with a very good precision using TLA plus syntax. So once you get used to TLA plus, you just prefer that. It's much more convenient. But from the learning curve point of view, there is this sharp learning curve to, because the syntax and how the spec is structured looks very different in TLA plus. So it's easy to start Pascal route and then gradually get more acquainted with TLA plus.
Then there is another question. Can you elaborate a bit on the consistency checker that you use to test the system? Did you use another formal methods as an engine for it? We used Jepsen, which is out there. We integrated that with our test infrastructure. And we used to do Jepsen runs in Cosmos for before doing deployment. Cosmos does weekly deployments worldwide of the entire stack, and use Jepsen pre-deployment as one of the pre-deployment gates. The consistency checker that we have is far more is much better integrated with the rest of Cosmos system. Jepsen is used as a sort of an external system to do the validation, but the consistency checker service that we have, the native one, knows about Cosmos idiosyncrasies and injects failures, and also monitors the failures that are happening in the production workloads directly, and then maintains this entire history of all the transactions, and it's much more real time. And so the consistency checker service that we have, we use it in production. Jepsen largely used during testing phase. But those are the two approaches that we took.
Thanks. There's a question by Andrei Kuprianov. And maybe, since this is a workshop, maybe you want to introduce yourself in a word or two so that we get to know each other.
Yes, hello. I currently work at Informal Systems, and we also do work with TLA Plus. So we have this Apache model checker, and we do model-based testing based on this. So the question I want to ask is, how do you ensure that the spec and the code stay in sync? So like you wrote this initial spec, and then the code evolves, right? It's a living artifact. So how do you ensure that they synchronize?
That's a great question. I think I should have mentioned one of the things that has worked for that is, in the implementation files, keep a link to the spec and write comments saying, anytime you fix a bug in this file or change the implementation, here is the spec for the implementation here, and for wherever we applied in whatever components, we put a link to the spec, just like the wiki link that I shared in the presentation. Those links are embedded in the source files as well. So any engineer who goes and changes anything, at least as a reference. Also during the code reviews, there's always, I found, in a small group of people who, when they do the code reviews, they make sure that the right things happen, and they point to if there's a new hire or new engineer on the team who is not familiar with either the spec or where the specs are, or and just fixing a bug, then they will remind them of where to go look for. But you're right, there's no like a natural, like a automated connection. So putting a comment and hyperlink in the code has helped.
Yeah, thank you. So you have kind of a knowledge base that connects the spec and the code, right? So you can go forth and back. Yeah, thanks.
There's a follow-up by Marcus on that question.
There's one more before that. Do you model fault scenarios in your specifications? Yes, yes, we do, and we also do quite extensive after the fact testing, and then go back, and sometimes if you missed cases, then we update the spec. So there's a iterative loop. Follow up from Andre, compared to Cosmos DB, have you tried harder in Singularity to make sure the code implements the spec, or is one of the lessons learned from Cosmos was that spec code gap is not a major concern? I think that based on the previous experiences, we have sort of assumed that the things that we learned in Cosmos much later, like hiring engineers who have some background in TLA, or those kind of things were, or doing when we do postmortems, apply the rigor. These things were learned later in the evolution of Cosmos, but in Singularity we are employing it from the beginning. Making the code and the spec drift, I think because we have good group of people in both the projects, we have managed to, like I said, make sure that they stay in sync. But so far we don't have an automated way of ensuring it, except hyperlinking it in the source files and while doing code reviews, reminding people.
I want to add something to that. So when we convert a spec to code, we can at that time we can also convert some of the invariants to code as well. Looking at the Cosmos DB example that Dharma was giving, so when you're writing a spec to validate transactional correctness in TLA plus, one invariant you can write is you can create a transaction history, and your invariant is checking that the history is correct. And then Dharma talked about an example where in production system, the same invariant is getting validated. So when you're converting the TLA plus spec to code, if you convert invariant to code as well, you don't have to think so much of keeping these two things in sync. Rather, the code will get validated by the invariant that you have invariant validations that you have added there.
I also actually had a quick short question about that. So you mentioned that you used TLC as a kind of post-mortem analyzer when something goes wrong. So does that mean that you actually have a link from the logs or whatever the system gives you back to the TLA specification, or how should I understand that?
Those are manual, not the links from the log, but sort of manual. The engineer would know how to reverse engineer and connect and then use the tool. But the source code one is relatively easy to link with the spec. But usually when a bug is discovered or a problem happens, when there is an invariant violation, we would get notified as a part of running the service. We will get alerted, and once that bug is discovered, then we would make sure that the fix that we produce is validated. But there's no direct connection from the logs.
Thanks. So Ron raised his hand. Please go ahead, Ron.
I work at Oracle on Java, and I want to ask, so obviously you've used TLC to find some issues with your design, but have you seen what other benefits from TLA Plus other than using the model checker have you enjoyed?
I think the most one of the sort of unsaid or unsaid benefits, I think, is that it forces the clarity of thinking, as Leslie talks about, or I've heard Leslie talk about in the past. Because software development is a sort of a communal activity. It's a team thing, and precise communication of the design and thinking through all the edge cases. Design documents, when engineers write design documents, it's such a subjective thing when they can be loose or they can be very precise, and it depends on who authors it. But it's hard to enforce a level of rigor in Word documents that people write to describe the design. And the way they communicate is also varies so widely across engineers. But having a common vocabulary and a common medium to communicate the specification of the design, and then exchanging that information across as the team size grows, that has to scale, that everyone needs to be equally precise, because a lot of these components talk to each other and make assumptions about each other's design. And so these aspects are very sort of implicit and unsaid. They're there, but I think that because it's not an isolation that someone builds the entire system on their own, this ability for the author of the spec, it forces the author to think through all the cases and precisely capture the design. And for the team as a whole, it helps in terms of exchanging that design, again, communicating precisely. People, when they do the design reviews, can ask the questions with equal level of precision, and then the spec can get revved up over time based on the feedback. So I think that as a tool to communicate design also, I think it's useful in terms of thinking through all the cases. It is vital. And that also sort of, as more and more people build that kind of way of approaching the design process, I think that makes the design process bar for the design process also raise collectively. So these things are, I found as a team lead or as an architect or as an engineer on the team, I find these things are not talked about, but they are there, and I think that they are very vital in making sure that the right things happen. I've heard Leslie talk about it in the past, but in terms of like real world team culture, I think it has engineering culture. It has a huge significance.
How many different people do you have at least reading the spec?
When we do design reviews, it depends depending on the components, but sometimes 10 people, 15 people, sometimes even more, 30 people, if it's a very critical piece of the system that touches everything. And also it is shared, as an artifact. It's there in the repo. People can browse it, read it, ask questions. Every new hire who joins the team, right? Once the system becomes so big, millions of lines of code later, like no one can keep the entire system in their head. And so when people join the team, or even though the people who have worked on the system for a long time, they don't remember all the edge cases, and so and Word documents there is a significant drift between the design, the implementation, and the Word documents people may have written. But these things are kept more or less in sync and are very precise in nature, so helps.
Thank you.
Thanks. Giuliano also raised his hand. Giuliano Losa.
Yes, hello, I'm Giuliano from Galwa. So I have two questions actually. So the first is, I think you mentioned that you expose TLA plus specs to your clients through SLAs, and do you have examples or where clients actually use the spec or understood them? That's my first question.
Yeah, so for consistency levels, which is a part of the service level agreement, we publish the specs for the consistency levels that Cosmos exposes, and application authors can consult those specs to know exactly what guarantees they are going to get. Because eventual consistency is a very vague term. There's to precisely specified or bounded staleness. What does that mean? And there are many overloaded assumptions when people talk about these terms of session consistency. What is the scope of a session, or what does that mean? So those specs help application writers to know what guarantees they're going to get.
But so you have evidence that they actually read the TLA plus or maybe run TLC and understood them?
Right.
Great, that's very impressive. And so my second question is there also, what would be the number one feature that let's say TLA, the TLA tools or TLC are missing and that would make your job easier?
I think the best way to find that is we can do an internal poll across the team and like stack rank the features. But the point that was raised earlier about having some connective tissue between implementation, because they are two separate islands and there's no connective tissue between the two. It happens very frequently, and we constantly, go back and update the spec and those kind of the tooling integration in the IDE for connecting the two would help get more adoption and more spec-driven development rather than people starting with the code first or changing the code or implementation without updating the spec. But we can post a stack rank list of the feature asks.
That'd be great to see. Yeah. Thank you.
Okay, Annie, please go next.
Oh, hi, Annie Liu from Stony Brook. Thank you for the talk. I also have two questions, and they are also actually related to some previous questions asked. You mentioned, one is how many people, right, I don't know, at Microsoft or at Azure or are really expert or at least in charge of writing TLA specs? Right.
In every team, I think in every team there is I know that Azure Storage, networking, Cosmos, IoT, like in every team it starts with a few people, and they sort of grow the base. It is not where we want it to be. It's not that we have an entire team of TLA plus experts in any one of these teams. But we also found, I was Vaibhav and I were talking a few days back, and he mentioned that one of the things here is that we don't need like the entire team to know TLA plus as a sort of a prerequisite to start writing specs. Only a few people who usually designers or architects or tech leads who are doing the design work, if we get that core group to adopt TLA plus, I think it goes a long way. But we don't have the entire team well versed with TLA plus. We haven't reached that level of adoption yet. But at the same time, every team is slowly building that awareness and sees the value and adopting it. That's my observation.
And are all these people trained internally at Microsoft, or they were pre-trained from some other program somewhere?
So Leslie had done a workshop there, and also the videos, the tutorials. I think we have distributed it internally. We have an internal alias where people post questions. So there's a community of folks who are plugged in.
When you're hiring new people who happen to have some students who know TLA, would that be a plus or not?
That's definitely a plus. And in fact, in the last 2 years, we hired externally, and Murat, who was a visiting researcher in the Cosmos team, also wrote specs. He also gave talks, and his students. Also, Murat had taught them TLA Plus, and when they joined Cosmos, and we made them full-time offers, they brought that knowledge with them, and they helped sort of spread it within Microsoft as well.
Thank you. My second question actually is also related to what I think Igor asked. You said you model, of course, when you're doing tests, you model failures. How are the failures specified? Are they just in the code, or I don't know.
So we have depending on the system, we have built failure injection systems at Microsoft, okay, depending on the services, because the cases differ. But the set of things are common, like network failures, injecting, disk failures, network failures, crashes. There is a sort of a common set of such primitives, but there are, based on the type of the service, like Singularity versus Cosmos versus IoT and other services, storage, they have specific correctness conditions, and they inject failures. So most teams inside Azure do this. They have a fault injection service of sorts that they use internally.
So the main programming language for those are C++, or?
Yeah, for the fault injection service itself.
Uh-huh.
For the all the infrastructure services like Singularity or Cosmos or storage or networking, largely C++. The fault injection is done in C#. It done in Java. Done in variety of languages.
Okay, thank you.
In Cosmos, it was C#.
Thank you.
So Leslie had a follow-up question to one of the questions that Annie asked, so maybe he should go first.
Okay, I might as well correct the spell at typing a mistake. What's the ratio of people who write TLA plus specs to people who just read them? And how much easier is it for people to just learn to read them if they don't have to write them?
I think that is a great question. There are far more readers than writers. I think that, and also the second point is also valid, that I find, and I'm not sure the exact, I haven't debugged the exact reason, Leslie, but it's easier for culturally telling people that, hey, because once the spec is produced, and if you set up a design meeting where everybody reviews the spec, then that is a forcing function perhaps for building a community of readers, versus like writing the spec. There is someone has to write the spec, and so that is a special effort on the part of the writer. So, but reading has been there are more people who read it, and it seems that it is easier just based on the number and perhaps it's a side effect of the activity, because there are only a few people who design the things and then others sort of critique it, versus everybody designing constantly in parallel. But definitely more readers.
Thank you.
So Terence Ford posted a question.
Which one?
I'm Terence Ford. I work at a company called ScreenMeet. We've just started using TLA Plus for some of our distributed problems. So I'm mainly interested in your consistency checker module that you mentioned. And if you discover a problem in production, are you able to somehow record that and prevent the regression in future releases?
Yes. Yes, so consistency checker detects the consistency violation and it has to do it for a customer's Cosmos database. So every database has its log, and consistency checker is doing it for every database of every customer, checking for violation. And whenever there's a violation, it is reported transparently in the Azure portal. So like we publish all the metrics. So high availability, local high availability, worldwide availability numbers, read versus write availability, consistency, latency. This less than 10 millisecond at P99 within the same data center client server end-to-end latency is measured and reported constantly as metrics for every database of every customer. So whenever there is any violation, it will tell that the expected SLA was this much, and this is a violation. And by the time it is reported to the customer, which is in real time, we also get an alert as a team behind the scenes, and some engineer will wake up and identify that this has happened. And then the goal for us is that depending on the criticality, either the bug is hot fixed very quickly, or in the next week's deployment train, the fix will get deployed to all customers worldwide. So this constantly happens, and these checkers in production detect it, and there's an SLA internally we have for time to detect and time to mitigate in a manner that it doesn't create like a widespread outage. So as much as possible, things self-heal, especially for availability related issues. But if there is a correctness bug, then very likely the fix would be very involved as well. And so these things get reported and we'll fix it.
I was just basically wondering if there's a way to recreate the behavior in the lab, so to speak.
Yes. For many of these issues, not just the consistency checker has to keep the history of the log, but of all the transactions. But for any issue that happened, we have our own logs for the telemetry that we emit from the code itself, right? So the engineer would be able to go and trace through the causality of the problem that happened, and would be able to troubleshoot. In fact, that's the only way we can troubleshoot any issue in production, right? So.
Gotcha. Thank you.
There's another question by Lazaro. You want to go ahead?
Hi, Lazaro.
Yeah, sorry, fighting my mute button here. So there were lots of questions on how to keep the spec and the code in sync, right? And I was wondering if you had come up with any best practice on how to do that. For example, I don't know, let's say one action, one function, or one line of the action, one function. And do you think that this kind of pursuit is any useful?
Could you explain? What do you mean? From the code going back to the spec?
Or from the spec going back to the code to make it simpler to relate both. Do you have any rules of thumb to say, okay, if you have one function, this should correspond to one action or one line of the code or something like that?
Right. No, we don't have that level of like a consistently done mapping because it depends on the implementation. Could get, the spec also, what level of information the spec captures, so like what abstraction that we describe the invariants versus the implementation. But I found that from the code going back to the spec to connect is usually more useful. The spec is like the sort of the blueprint, and then we go into implementation so we can consult the blueprint. But from the blueprint, there's so much detail, and it depends on how the code is structured and modularity of the code itself. So intuitively, at least for what has worked so far, is the reverse mapping.
I see. It makes sense because, at least from my point of view, the TLA is so powerful, right? That with just one line you can write really big behaviors, describe really big behaviors, right? Yeah, but I just wanted to be sure. Thanks.
Cool. Thank you. Thank you so much. It's so great to see everyone engaged, and thanks so much for having me.
Yeah, thank you. I don't know. So if we still have time for 1 or 2 questions.
Sure.
Would that be okay?
Yeah.
So Marcus had another question.
Hi, Marcus. I work on TLA Plus, and tomorrow there will be a number of talks about code and specs and how to bridge the gap. One thing that you mentioned, Dharma, is you also use Jepsen, right? Or Cosmos DB uses Jepsen. Is there some input from a TLA Plus spec into Jepsen? Is there any kind of knowledge transfer or even a more formal transfer between those two, or is it just 2 separate things that live in isolation?
Yeah, they are 2 separate things, live in isolation. We wanted to make sure that because Jepsen was used across databases, and we wanted to make sure that we don't use it like once in a blue moon and like declare victory, but we use it as a part of our test automation. And so that's how it got integrated. But they are separate islands right now. But it's a good point, Marcus, if you do a deeper integration of Jepsen in the system, like that consistency checker, then we could perhaps connect the 2 better.
Yeah, thanks.
Igor, you want to go next?
Hi, yes. Hey, my name is Igor Konov from Informal Systems, and we are also using TLA quite a lot now. So my question was, what do you do when TLC doesn't come back in reasonable time, like after a couple of days, weeks? You already mentioned that you should decompose the problem,
right.
But sometimes you just cannot decompose some algorithms, like consensus, for instance. Do you have any insights? How would you approach that?
Vaibhav can speak more, but I think that so far we've managed to decompose all of our problems into more, building block, smaller building blocks, and then check them in isolation before composing them into a bigger molecule.
I think at that point, the best way is to debug how where the state space explosion is happening. I think Marcus has something more to add. Yeah, Marcus.
I have kind of a follow-up question, which is, have you run into bugs that couldn't be found under the small model hypothesis? That bugs are found by a small model that TLC perhaps can handle, or Apalache. Other bugs that simply couldn't be found by the small model hypothesis and required a super large model that was outside.
No, I don't think so, because essentially a large model is simply the multiple small models just put together. The contract is still, it's something like this, right? Your when you write a large model, you're just multiplying states of two small model. The functionally doesn't really change. So I haven't seen a problem where it will be any way different in terms of behavior. Most of the cases where we ended up with a large model was either we did not think that the model will evolve to something that big, and it was just the result of gradually model becoming very large, and we did not get time to optimize it again. Or very early model writing, someone started one from scratch and ended up with a large model, something like that. But if you plan it from the beginning, it's easy to decompose. I think I haven't seen a problem where it's not possible.
Thank you. Let's just take one last question. There's one on the chat by Naul Duga Gevesa.
Stefan, are you looking for a question or?
Well, yeah, maybe the participant.
Oh, sure.
No, here he is. Yeah.
Oh, yeah. Hey, great talk. I really enjoyed it. Thank you. I had a question about change in version control, between the spec and the implementation. And of course, you have it deployed. So do you have, assuming you are using Git or something like it, do you have some kind of pattern, for collaboration, like Git flow or something like that?
That's a great question. What we've done is because specs are checked in our repo and the code is there, and we know where to find the specs, right? It's if you have the implementation of the transaction manager, then the spec for the transaction manager would be found next to the implementation of it. And in the code of the main module of the transaction manager, we would link the spec from there. So that kind of structure is there. And then on the team wiki, which is also bootstrapped from the repo, it is there for new hires to discover specs easily. That level of sort of manual structure we have. We don't have like a automated pipeline of like because there is still a human involved, the designer involved who has to design the spec. Then there are engineers who will implement the code. So it's not automated, but it's a neat idea if we can create some pipeline infrastructure.
Thank you. Thank you.
Okay, so thank you really very, very much for your great talk and also for the long discussion. Many questions shows that people are really interested. So thanks a lot.
Thanks so much. Thank you.
So yeah. So we'll continue tomorrow. So this is virtually in the Central European time zone, right? So we're continuing at 3 p.m. Central European time tomorrow, whatever that means for you. So be aware, please, that the Zoom link will be a different one tomorrow. So please go back to this for participants page of Disk to find the appropriate link for tomorrow. I don't know what it's going to be. If you have any suggestions on how to run the workshop, on improving it and so on, please leave your thoughts in the chat in this virtual hallway on talk@tlapl.us, because the Zoom chat will be gone, obviously. So if you write something there, we won't get the message. Leslie, anything to add?
Well, I want to thank Dharma for a great talk. I certainly learned a lot about how TLA is being used in Microsoft. And thank you, Stefan, for taking care of the Q&A and for starting the next sessions at an hour when I'll still be in bed. So,
Okay.
So
We'll
long,
see you.
everyone.